Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of unit electric charges and field. Let's begin. First, we will discuss about the types of electric fields. There are different kinds of electric fields. So we can on a majorly define them or segregate them as a uniform electric field, a non-uniform electric field, and radial electric field. If you remember in previous classes we have defined the electric field, what it would be. Did you remember this? Yes, it's a force on a unit charge. And which kind of charge I was taking for the test charge? Positive charge or negative? Think. Yes, it's a positive test charge, so it is an F by Q naught. Now, in types of electric field, we generally define three kinds of electric field. First is the uniform, another is the non-uniform electric field, and the last is the radial electric field. Now let's look what are the uniform electric fields look like. So in uniform electric field, how can I define it? When I say ki magnitude as well as direction, both of the electric field intensity is same at all points in a space, then the electric field is said to be in a uniform electric field. Now look at this. Separation between two lines at every place is equal. So as I know field is the vector quantity, so it should be having both, should be a same. It should be having a same magnitude as well as same direction. So if magnitude and direction of the electric field is same, then that electric field is known as the uniform electric field. Now what are the non-uniform electric fields? When magnitude and direction of electric field intensity are different at different points, then the electric field is said to be non-uniform electric field. Now look at this. Here direction is changing. Here direction is changing. Even separation is changing. Look at this. This separation and this separation. Even let's say a electric field given like this. Even this is non-uniform electric field. Let's say electric field lines are given like this. Look at the separation. So even this are said the non-uniform electric fields. I hope this seems clear. And last, it is a radial electric field. It is a radial electric field. So in which, let's say at this point charge is given and the field is directed towards or away from the same fixed point, then this electric field is known as the radial electric field. Now why we discuss all this at this point of time? Why we discuss all this at this point of time? Let's look and begin. First, let us say that what we need to do is I need to put a electric dipole in uniform electric field. Now you know what is uniform electric field, having a electric field having the same magnitude and direction. Let's say this is electric field. Their separation is approximately equal, and I have put up a dipole. This is the dipole. This is the minus q charge. This is the plus q charge. Let's say this is the reference line, and this is the angle theta. I have put up an electric dipole in uniform electric field, and I need to consider a force on this. Now, did you remember this? When I have defined electric field, it is an F by Q. Yes. So if I need to find out the force, I can write like this. It is a Q into E. So here it is a positive charge. Here it is a positive charge. So force on the positive charge will be in the same direction as that of the electric field. I repeat, force on the positive charge will be in the same direction as the direction of electric field. So force on this would be look like this. Force on plus q. So it is obvious that when positive charge is having a force in same magnitude, negative charges would be having in opposite direction. This is force on minus q. Would it be clear? Would it be clear? Yes. Now what would be the magnitude of this force? It is a q into e. What is the magnitude of this force? It is again q into e. So if I have been asked what would be the net force, what would be the net force on a dipole when placed in uniform electric field, I can say it's in plus QE minus QE. Both are having same magnitude but opposite direction. So it's that's why it is zero. So that's why this comes to us now. Now this dipole having a net force zero, but does it have a torque? Think over it. Does it have torque? On a very first note, do you understand torque? What is it? Yes, you guess it correctly. It is the force multiplied by perpendicular distance, and it is the rotational analogous. It is what we say as a rotational analogous of a force, which tries to rotate this dipole. Let's look how this torque behaves and what would be its magnitude and what would be its direction. Let's say we will find out the torque acting on electric dipole when it is placed in uniform electric field. This is our dipole, this is minus q, this is plus q. Their separation is 2l, and electric field is in this direction. Electric field is this direction. What I need to find out, I need to find out the torque. What is it? It's an force multiplied by perpendicular distance. Now, as I know, this is 2l. This is the length of a dipole. This is 2l. So if I consider this length, that should be 2l cos theta, and this would be 2l sin theta. Yes, as I mentioned, sin theta is equals to AC by 2l. So perpendicular distance AC is equals to 2l sin theta. Now when I need to apply torque equals to force multiplied by AC. Now what is force? In previous slide we have done this, that force is equals to Q into E. So this is Q into E multiplied by 2L sin theta. So if I rearrange this, I just rearrange this. This is Q into 2L. Let's put up into one bracket, multiplied by E sin theta. Now what is Q into 2L? Remember the dipole moment? Dipole moment. What was it? It's an it's an charge of multiplied by separation between two charges. It's a q into 2l that I can write as in dipole moment p. So this is p multiplied by e multiplied by sine theta. So I can write like this: torque equals to p sine theta should be equals to torque equals to p cross e. It's a cross product, and mind well, when there is a cross product, your answer would be a vector. Yes, torque is a vector quantity, that you know. Now, when theta is equals to 0, now first thing, what is the theta? Theta is the angle between, theta is the angle between dipole moment P and electric field E. Theta is the angle between P and E. So torque equals to P sin theta. When theta is equals to 90 degree, then sin 90 is equals to 1. So torque equals to P into E. It is a maximum. And when theta is equals to 0 degree, when theta is equals to 0 degree, then torque would be equals to 0. This is the minimum value of the torque. Got it? Yes. So this is torque acting on a dipole when it is placed in uniform electric field. Now let's find it out. If we try to rotate, the dipole, what would be the energy stored in electric dipole, or rather we should say what amount of work done to be needed. Let's look at the situation. This is our dipole, this is minus q, this is plus q, and this is the separation between these two charges. We are having an electric field in upward direction. So as I said, on positive charge, force is acting on the same direction in which electric field is applied. So this is plus QE, and on negative charge, force is applied on opposite direction, of the electric field. So what I know is we know that dw is equals to pe sin theta d theta. Do you remember this? From how could I calculate this? So let's look. Can I write work done is equals to force into displacement? Can I write work done is equals to force into displacement? Now look at very carefully. If I write this, if I want to write a rotational analogous of this, then I can write this force, rotational analog of force, it's a torque, and rotational analogous of x, it's a displacement, it is angular displacement. So work done is equals to torque into theta. When I consider a smaller amount of term, I can write this dw is equals to torque into d theta. Now what is torque? What is torque acting on dipole? It is P E sine theta. So this is dw is equals to torque. This is P E sine theta into d theta. Does it make it clear? Yes. So I can write as dw is equals to P E sine theta into d theta. Is it clear up till now? Any doubts? Okay. Now let's integrate this. Let's integrate this. So I need to find out the total work done required. I need to find out the total work done required. I need to find out the total work done required to rotate with angle 90 degree to 0 degree. So how could I do this? Give me a 1 minute. I need to find out total work done to rotate with an angle theta from 90 degree to theta. So let's integrate this on both the sides. So this is dw, and if I integrate this from the 0 to w, and I integrate this from 90 to theta, so what this comes is, this is w is equals to pe sine, integration of sine theta is minus of cos theta, and let's put up a value 90 degree to theta. So this is equals to minus at this position and cos theta minus cos 90. So this data comes to a w is equals to minus of pe into bracket cos theta minus 0. So this work done is equals to minus of pe cos theta. As you might know that this work done will store in the dipole in the form of potential energy. So this is potential energy stored in a dipole. This is potential energy stored in a dipole. I can write like this, minus of pe cos theta. This is minus of p dot e. You might remember this. This is a dot b, when and when it would be. I can write like this, a dot b is an ab cos theta. So this is minus of pe cos theta. I can write like this, minus of p dot e. Does it clear? So up till now in this class we have discussed two things. One is the torque acting on dipole. One is the torque acting on dipole when it is placed in uniform electric field. And the another thing that we have discussed is potential energy or work done required to rotate the dipole. Okay. So here what we can do one more thing. What we can do one more thing is, if I put up a different angles, then work done is equals to minus of PE into cos theta. Let's look at this. Here I have taken from 90 degree to theta. Here I have taken from 90 degree to theta. If my limits were from theta initial to theta final, what it would be? So this is equals to minus of PE into bracket cos of theta final minus cos of theta initial. I can rearrange this such as this, cos theta initial minus of cos theta final. This is the work done. And one more formula, minus of PE cos theta. So this is applicable for any angles. This is applicable for any angles. This is applicable only when theta initial is 90 degree and to theta final is theta. So you need to remember these two questions, these two formulas. One is the work done is equals to P into E into cos theta initial minus cos theta final, and another is the work done is equals to minus of PE cos theta. First relation you will is you will use when and when they have been asked about the any angles. Let's say they have asked that dipole is rotated from 30 degree to 60 degree, then you need to use work done is equals to PE into bracket cos theta initial minus cos theta final. But now let's suppose they have been asked that dipole has been rotated from 90 degree to 45 degree. So when initially it is at 90, you can just put it down minus of PE cos theta and theta would be a 45 degree. I hope these things are clear. So we have done two tasks. One, electric dipole in uniform electric field, it would be having a torque, it would be not having a force, or net force would be a zero but net torque would not be a zero. What would be the net torque? The net torque would be equals to PE sine theta, and when it has been rotated, certain amount of potential energy would be stored in that dipole. That potential energy would be given as work done is equals to minus of PE cos theta or PE into bracket cos theta initial minus cos theta final. These are the situations. Okay, let's look at certain cases. Let's look at the certain cases. Let's see. This is the electric field E, and I have put up a dipole like this. Yes. So here, angle between P and E is 0 degree. So what is torque? Remember, torque equals to PE sine theta. This would be a 0, as sine 0 would be a 0. And what would be the potential energy? It was minus of PE cos theta, as theta is equals to 0 degree, cos 0 is 1. So this is minus of P into E. Yes. Next, let's suppose situation looks like this. This is the direction of electric field, and this is the dipole. It's a P. Here angle between P and E, angle between P and E is 90 degree. What is the torque? It is PE sine 90, while sine 90 would be a 1. This is maximum torque. This is maximum torque, torque max. And potential energy, it's a minus of PE cos 90 would be a 0. This is the second case. And let's look at the third case. While the situation would be look like this. This is the electric field, and this is the dipole moment P. Now here angle is 180 degree. Here angle between P and E is 180 degree. What is torque? P E sine 180. Sine 180 is 0, so the torque is 0. What is the potential energy U? What is the potential energy? It's a minus of PE cos 180 degree. Cos 180 is minus 1, so this is plus PE. This is what we say as in plus PE. Does things are clear up to this? Does it clear? Now remember one thing. Remember one thing. In class number 11, you have studied maximum minimum, as well as you have studied the stable equilibrium and unstable equilibrium. Now first thing, what is equilibrium? We say when and when object is in rotational or linear equilibrium. Equilibrium means when it is having a net force as 0 or it is having a net torque 0. It is having a net force 0 or it is having a net torque 0. Here we are talking about the torque. So when it is having a no torque, then it can be considered in equilibrium. I mean, we are talking about the rotational equilibrium. So here torque is 0. Even in this case torque is 0. This potential energy is minimum. When potential energy is minimum, when potential energy is minimum, your particle, your system, here your dipole is in stable equilibrium. Do remember this thing. Your dipole is in stable equilibrium. Here this potential energy is maximum, so here it is in unstable equilibrium. So if theta is equals to 0 degree, this represents stable equilibrium. If theta if theta is equals to 180 degree, if theta is equals to 180 degree, do remember these things. If theta is equals to 180 degree, then it is in unstable equilibrium. Yes, do remember this. Now stable equilibrium when theta is equals to 0 degree, and unstable equilibrium when theta is equals to 180 degree. So everything is clear. We have discussed about the torque, we have discussed about the work done or the potential energy stored. Now let's go through the numericals of the situations. Let's say first question. Find out potential energy stored in electric dipole when it is rotated from stable equilibrium to unstable equilibrium. Now first, what is work done or potential energy stored? It is PE into bracket cos theta initial minus cos theta final. This is a subscript for an initial, this is a subscript for a final. Now you need to rotate this from stable equilibrium to unstable equilibrium. When it would be at stable equilibrium, theta would be a 0, and when it would be at unstable equilibrium, theta would be 180 degree. Now let's put this value. This is PE into bracket cos of 0 degree minus cos of 180 degree. So this is equals to P into E, cos 0 1 minus cos 180 minus of 1. So this is equals to P into E into bracket. This is 1 plus 1. So this is twice of PE. This is twice of PE. Clear? Got it? Yes? Any doubt? Any doubt? No? Very good. Well done. So let's move to the next numerical. Let's say this is the uniform electric field. Your dipole was in this situation initially. You can see this is 90 degree. Now it has been rotated by certain angle, and that certain angle is 30 degree. You need to find out ratio of torque acting on dipole to work done required. Now first, what is torque required? What is torque required? It is a PE sine theta. What is the work done? It is minus of PE cos theta. This is minus of PE cos theta. I need to find out the ratio. So let's begin. Torque, this is equals to PE sine theta. Potential energy or the work done, you can say, is this is minus of PE cos theta. This would gone. So this is equals to minus of tan theta. This is equals to minus of tan theta. And as as per the data, this theta is 30 degree. As per the data given, this theta is equals to 30 degree. So this is equals to minus of 10 30 degree. What is 10 30? It's a minus of 1 by root 3. This is the ratio, torque to the potential energy or torque to the work done. Yes, will you be comfortable with these things? Yes, yes, will you be comfortable? Are you sure? Okay, so let's move to the next topic. Electric dipole in non-uniform electric field. Now, did you remember what is non-uniform electric field? Yes, we just said it that when magnitude or direction or maybe both are changing, then the electric field is said to be a non-uniform electric field. First, let us understand what are the sources of non-uniform electric field. What are the sources of non-uniform electric field? Let's say this is point charge q. Let's say this is point charge q. Electric field due to this point charge will be uniform or non-uniform. How can I find it out? How can I find it out that electric field due to a point charge, electric field due to a point charge will be a uniform one or non-uniform one? So just go through its data. Its formula, it is an E is equals to kq by r square, where r is the distance. So if I put r is equals to 1 is equals to E is equals to kq. If I put r equals to 2, it is kq by 4. If I put r equals to 3, it is kq by 9. If I put r equals to 4, it is kq by 16. So this point charge provides non-uniform electric field. Point charge provides non-uniform electric field. Do remember this thing. So now let's put up a dipole. Let's put up a dipole into the electric field provided by a point charge. Let's suppose situation is something like this, and the separation between these two is r. Separation between these two is r. I need to find out the torque acting. On a very first, I need to find out the torque. What is torque? How could I find it out? Think. Do you know the formula of torque? Yes. What is it? It is P into E into sine theta. What is theta? Theta is the angle between P and E. So let's check it out. This is the P. Here it is a point charge and it is a positive point charge. So direction of positive point charge will electric field due to point charge is in this direction. Yes. Now this is P, this is A. Angle between these two, is 0. So torque would be PE sine 0. What is sine 0? What is it? 1? No, it's a 0. So torque would be a 0. So here in this case it is not having any torque. Here in this case it is not having any torque on the dipole. Now let's next look at the potential energy stored in a dipole. U equals to minus of P dot E. Remember this? Yes. Theta is 0. Theta is a 0 degree. So this would be minus of P into E into cos of 0. And when I write minus of P into E into cos of 0, it's a minus of P into E. So potential energy would be stored in the dipole. You can write like this. It's a minus of P multiplied by electric field. Which one provide the electric field? This point charge. What is the electric field due to this point charge? I can write like this. It's a KQ by R square. And if required, K can be replaced by 1 upon 4 pi epsilon naught. So this two are the things. Now last and very important, very important, what is the force acting on the dipole? What is the force acting on the dipole? So in 11th class you have studied this relation. F is equals to minus of du by dr. U represents here the potential energy and R represents the distance. So if I do this, this is minus of d by dr of, look at this, this is kpq by r square, kpq by r square. So I can write like this, it's a kpq into d by dr of r square, so r to the power minus 2. If I write like this would be minus of kp cube multiplied by 2 divided by r cube. This is the force acting. So basically we require these three things. We require torque, we require potential energy, and we require a force. So what is the conclusion? Before going to conclusion, let's just look at as a simple case 1, and we will get back to this once we go through the next situation. But if we discuss this, the torque would be a 0 and force is the non-zero. Torque would be a 0 but force is the non-zero. Got it? Now let's move to the next situation. Case 2. Suppose this is point charge plus q and dipole is something like this. This is plus q, this is minus q, and I am interested in torque. Just with the help of diagrams. So here force on F1 would be acting as this is a positive, and here this force on the negative charge would happen. This is F2. So in this situation, even force is not 0, even torque is not 0, because these two forces will rotate the dipole. So there must be net torque. There must be net torque on the dipole. There must be net torque on the dipole. Yes. So in this case, even force is not 0 and torque is not 0. Yes. Comfortable? Yes. We are discussing about the electric dipole in non-uniform electric field. Yes. And as a source of non-uniform electric field, we are taking the point charge because it is a source of non-uniform electric field. Okay. So Now let's move to the let's move to the one more question. Do it very carefully and try to understand this. Let's say this is first dipole P1. Let's say this is another dipole. This is P2. And the separation between these two is R. I need to find out torque on torque on dipole P2 due to due to dipole P1. Now what you should do? Tell me. Torque on dipole 2 due to dipole 1. How could you manage it? Think. First, write down the relation. The relation would be torque equals to P2 into E1 into sine theta. Remember this thing, very important. Dipole would be mine. Electric field will be provided by someone else. I need to find out torque on P2. So when I need to find out the torque on P2, I need to write a dipole moment of myself. It's a P2. But on me, force would be applied by some other source. So it's an electric field by P1. It's an electric field by P1. Now, for P1, remember these things, please. For P1, this point is at equatorial position. This is at equatorial position. Do you remember these things? And for equatorial position, electric field will be opposite to the dipole moment. So in this direction E1 would be there. In this direction E1 would be there. So here in this case theta is equals to 0 degree. When theta is equals to 0 degree, I can find it out. Torque equals to P2 multiplied by E1 into sine of 180 degree. And when I write sine of 180 degree, I should write it as in minus 1. Sine 180 would be a 0. Yes, it is not in minus 1, it is 0. So sine 180 is 0 and the torque would be a 0. Yes. Want to go beyond this? Let's find it out, the potential energy. Theta is equals to 180 degree. Is it clear? Now let's look at the potential energy. What was its formula? U is equals to minus of P2 dot E1. This is minus of P2 into E1 into cos. Here the case is 180 degree. So this is equals to that should be P2 into E1. Here minus is already there and cos 180 comes to 1 minus 1. So this is equals to plus P2 multiplied by E1. Now what is the electric field due to this dipole? It is at the equatorial position. So at equatorial position the magnitude of E1 would be K P by R cube. Here it is P1 divided by R cube. So this is K P1 P2 by R cube. So we have find out this two things: torque on P2 due to dipole P1 as well as potential energy stored. First, second. Find it interesting? Would like to go through the next step? Are you sure? So let's find out force as well. Let's find it out, the force as well. Situation was like this. This is P1, this is P2. And their separation were given as R. You need to find out the force. On P2 due to P1. you need to find out the force on P2 due to P1. Now F is equals to minus of du by dr. We have used it before as well, so you know how this comes. So this is d by dr of potential energy. What is it? Let's look. It's a k p1 p2 divided by r cube. This is k p1 p2 divided by r cube. So this all are the constant. Keep it aside, p1 p2, and this is equals to d by dr of r to the power minus 3. So this is equals to minus of minus 3 multiplied by k multiplied by p1 into p2 divided by r to the power 4. So if I rearrange this, this would become minus minus plus 3k p1 p2 divided by r to the power 4. Remember this. This is very useful. Yes. So we have done three operations. First, torque acting on dipole. Second, potential energy stored on a dipole. And the third, force acting on a dipole due to other dipole. So let's summarize this. Dipole dipole interaction. Do remember these things. Very important. Let's say first dipole is like this, another dipole is like this, then torque is 0. U is directly proportional to the 1 by r cube, where r is the distance between these two. U is the directly proportional to the 1 by r cube of the separation. This is the separation, and this is true for any category of dipoles. This is true for every dipole or every configuration of a dipole. And last but not the least, and very important, force between two dipoles is F directly proportional to the 1 by R4. This is the favorite one of the paper designer. Do remember these things. F directly proportional to the 1 by R4, or F inversely proportional to the fourth power of distance between these two. They have asked it so many times in many examinations about the force. What are you getting it? Yes, this is the dipole dipole interaction. I would like to summarize one more thing. That is dipole placed in electric field of point charge. So let's say this is point charge. This was the dipole. Then its potential energy is inversely proportional to the square of the distance. Remember this thing. And its force is 1 by r cube. Do remember these two things. These are very important. Do remember these two things. This is the interaction between dipole and point charge, and previously it is the dipole dipole interaction. So here it is U inversely proportional to the r cube and F inversely proportional to the r to the power 4. And here that means an interaction between a point charge q and dipole p. It is the potential energy which is inversely proportional to the square of the distance, and force, it is the inversely proportional to the cube of the distance. Yes. Can we move to the next? Did you remember this? Are you sure? Let's look at this. Go through the question. Now, if dipole is placed in electric field of a point charge at distance r, then force acting is F Newton. If distance doubles, find new force. Do it on your own. Do it quickly. We must know that F is proportional to the inversely proportional to the cube of the distance. So now they what they did is they make a distance doubles. So I can write F dash by F. This is equals to previous distance. This is 2r cube because they make it double. So this would be r cube divided by 8r cube. This r cube gone, and the remaining things the remaining things is 1 by 8. So this is the ratio. F dash is equals to 1 by 8th of the previous force, F by 8 Newton. Yes, very easy. But for that you need to remember this. If you are through with this, you can do it in a fractions of seconds. Let's take a one more numerical. It's a P1, it's a P2. Their distances are. In this situation, force acting is F Newton. Now, situation looks like this. This is P1, this is P2. The separation is 2r. Now, find force F dash. This is the requirement. This is the requirement. So I know when and when it is a dipole-dipole interaction, when it is a dipole-dipole interaction, the force is related with the fourth power of the distance. So now I can write like this: F dash by F. This is equals to r to the power 4 divided by 2r to the power 4. So this comes to an r to the power 4 divided by 2 to the power 4. This is 16 times of r to the power 4. So this comes is F dash should be is equals to F by 16 Newton. This would be the answer. This would be the answer. Yes, can you get it? Does things are clear up to this? Are you sure? Are you sure? Pretty sure? Okay, let's move to the certain theoretical questions. When dipole, when dipole is placed in uniform electric field, when dipole is placed in uniform electric field, its F net would be equals to 0 for sure. Torque net may or may not be 0. Why? Torque may or may not be 0. Why it is like this? If I considered theta is equals to 0 degree or theta is equals to 180 degree, then torque would be a 0. And if theta is equals to 90 degree, then torque is maximum. So remember these things. Remember this thing. If dipole is placed in uniform electric field, then for sure shot, F net would be a 0. But torque may or may not be 0. When it would be a 0? If theta is equals to 0 or 180 degree. If theta is equals to 0 or it is a 180 degree, then the torque would be a 0. But if theta is equals to 90 degree, then torque would be a maximum. It could not be a 0. And maximum torque means it's a torque equals to PE. Yes. Now what would be the situation when dipole is placed? If dipole is placed in non-uniform electric field, did you remember the case 1 and case 2 when dipole is placed in non-uniform electric field? Yes. So if that has been remembered by you, tell me, what is the F net? 0 or non-zero? 0 or non-zero? F net, it could be a maybe 0 or may not be 0. It could be anything. F net could be a 0, may or may not be 0. What about the torque? Even same thing. It may or may not be 0. So remember these two slides for the logical questions. They are the theoretical questions and that takes fractions of second to get it solved. So you need to go for this very quickly. So if it has been placed, if dipole is placed in uniform electric field, then F net would be 0 for sure. But torque may or may not be 0. It could be 0, it could not be. When dipole is placed in non-uniform electric field, then F net, again F net could be a 0, it could not be a 0. Why? Did you remember this? Yes, in case 1 it was the 0. In case 1 torque would be a 0, but in case 2 torque would not be a 0. And F is directly proportional to the certain distance. If it is a point charge, it could be a 1 by r cube, and if it is a dipole dipole interaction, it is 1 by r4. So these are the things. Now let's move to the next, that is, if electric dipole is placed in a uniform electric field, and let's suppose it starts oscillating in uniform electric field. I need to find out, I have been given that find out time period of oscillation if dipole is placed in uniform electric field and it performs oscillations of smaller angular displacements. Go through the data very carefully. Go through it. Take your time and do this. You have been asked to find out time period of an oscillation, for which they have put up a dipole. In a uniform electric field, and when they have put up this, they just want to find out the time period of its oscillations. So how will you do this? Let's say the situation would be something like this. Let's say this is minus of charge, this is plus of charge, this is the dipole, and maybe electric field will be in this direction, so it will start oscillating like this, plus q minus q, something like this or like this. So what could be done? Tell me what could be done. Do you remember the oscillations in class number 11? Do you remember it? Do you remember the conditions of oscillations? First go through this. Conditions of oscillations. At first condition, it would be A is equals to minus of omega square x. This is the acceleration and x is the displacement. This is linear acceleration. And the second is the angular acceleration. In that condition, you were writing it as alpha is equals to minus of omega square theta. This is angular acceleration, and this is angular displacement. This is angular acceleration and this is angular displacement. Now we are going to use one of this. How can we do it? Let's look at this. We know that torque equals to P E sine theta. Yes, they have asked for the smaller angular displacement. So if theta is very small, if theta is very small, then I can write that sine theta is approximately equals to theta. So what I can write is torque equals to minus of P into E into theta. Why minus? It is a restoring torque. It is a restoring torque. So what I can get is torque equals to minus of P into E into theta. Now torque is I alpha, is equals to minus of P into E into theta. Now as I know alpha is equals to minus of PE by I into theta. Alpha is equals to minus of P by I theta. Now compare this with the condition of angular SHM. It's alpha is equals to omega square minus of omega square theta. Look at this. Here it is alpha, this is alpha, this is theta, this is theta. So I can compare omega square with PE by I. Yes, now it is very easy that I can write omega as root of PE by I. I know that omega is equals to 2 pi by t. I'm sure you must be knowing this. Divide by PE by I. So this t is equals to 2 pi under root of I divided by PE. This is the time period. This is the time period of its oscillation if dipole is placed in uniform electric field. Okay, so let's check this very quickly. Factors on which time period depends. A very small kind of questions can be asked. Factors on which time period depends. The relation is t is equals to 2 pi under root of I by PE. So if all things remains the constant, t is directly proportional to the I. Other parameters are same. T inversely proportional to the root of the dipole moment. Again the same thing. Other parameters are the same. And last but not the least, t inversely proportional to the root of e. Other parameters same. So from here they can ask certain questions. If I change the I, what would be the change in time period? If I change the dipole moment P, what would be the change in time period? Or something like if dipole moment is double but electric field is half while the I remains the same, what would be the change in time period, and something like this. So this can be done, and that can be done very easily, and these are the fresh questions. Never ever questions has been asked from this. So there are fair chances that questions can be asked from this. Yes, so let's wind it up. What we have done in today's class, is we have started with the different categories of electric field. Then we have put up our dipole in a electric field, that is of uniform electric field. Then we find it out that what is the force acting, what is the torque acting, and what is the potential energy stored in the dipole. Then we have gone through the different cases of the stable equilibrium, unstable equilibrium. Then we have put up our dipole in non-uniform electric field. Even in non-uniform electric field, we have seen two different categories of electric fields. One electric field was originated by the point charge, while the other electric field was originated from the dipole itself. So it would be a two interactions, dipole and point charge interaction and dipole dipole interaction. You need to remember their formula. They will be very very helpful to you in your exams. Certain questions will be asked for sure, yes. Then at last we have did the oscillation. We make dipole to oscillate in uniform electric field. Again, it's an oscillation having a smaller displacement, and you need to remember its time period formula. It is 2 pi under root of I by P, where I is the moment of inertia of a dipole, I is the moment of inertia of a dipole, P is the dipole moment, and E is the electric field in which dipole oscillates. Yes, so let's shut it down. Please do a practice of this kind of questions. This will help you. Thank you. Have a good day. Bye bye. Take care.